But if we now have a way to represent all inputs in the world, be it letters, numbers, images, videos, anything else, and get output from some problem-solving process, like how do we actually solve problems? Well, the secret sauce in the middle here is another term that you've probably heard in the real world nowadays, which is that of algorithm, step-by-step instructions for solving some problem. So this ultimately is what computer science really is about too, is not just representing information, but somehow processing it, doing something interesting with it to actually solve the problem that you've been provided as input so you can output the correct answer. Now, there's all sorts of algorithms implemented in our phones and in our Macs and PCs, and that's all software is. It's an implementation in code, be it C++ or Java or anything else, other languages exist too, in code that the computer understands, but it's still just step-by-step instructions. And among the things we'll learn in CS50 is how to express yourself in different ways to solve problems, not only in different languages, but using different methodologies as well. Because as we'll see, among the reasons we introduce these several languages is you don't just learn more and more languages that allow you to solve the same problems. Different languages will allow you to solve different problems and even save you time by being better tools for the job. So here, for instance, on an iPhone is maybe a bunch of contacts, which is presumably familiar, where we might have a whole bunch of friends and family and whatnot alphabetized by first name or last name. And suppose we want to find one such person like John Harvard, whose number here might be +1 949 468 2750. Feel free to call or text him sometime. This is the goal of this problem. If we have our contacts app and I start typing in John's name by first name or last name, the autocomplete nowadays kicks in and it somehow filters the list down from my 10 friends or 100 friends or 1,000 friends into just the single directory entry that matches. So here too, back in the days of RG&B projector, we had phone books like this here too. I'm pleased to say, thanks to our friend Alexis, this is the largest phone book that we've used for this demonstration. This is an old school phone book that's essentially the same thing as our contacts app or address book nowadays, whereby I've got a whole bunch of names and numbers alphabetically sorted by first name or last name, whatever, and corresponding to each of those is a number. So back in the day, and frankly, even nowadays in your phones, how do you go about finding someone in a phone book or your contacts app? Well, you could very naively just start at the beginning and look down and just turn one page at a time, looking for John Harvard in this case. Now, so long as I'm paying attention, this step-by-step process will get me to John Harvard. Like, this is a correct algorithm, even though you might kind of object to how I'm doing this. Why? Like, what's bad about this algorithm? It's just slow. I mean, this is crazy slow. If there's like 1,000 pages in this phone book, which looks like there are, like this could take me as many as 1,000 pages, or maybe he's roughly in the middle, so like 500 pages. Like, that's crazy. That's really rather slow, especially if I'm going to do this again and again. Well, what if I do it a little smarter? Grade school, I sort of learned how to count 2 at a time. So 2, 4, 6, 8, 10, 12, 14, 16, 18. Again, if I'm paying attention, I'll get there twice as fast because I'm counting 2 at a time. But is that algorithm step-by-step correct? And I'm seeing no, but why? I might skip over John Harvard. So just by bad luck and kind of with 50-50 probability, he's going to be sandwiched between 2 of the pages. Now, I don't have to abort this algorithm altogether. I could just, as soon as I get past the J section, if we're doing it by first name, I could just double back 1 page and just make sure that I haven't missed him. So it's recoverable. And this algorithm, therefore, is sort of twice as fast, plus 1 extra step maybe to double back. But that's arguably otherwise a bug or a mistake in the algorithm if I don't fix it intelligently. But what did we do back in the day? And what does your iPhone or Android phone do? What they typically do is they go roughly to the middle, look physically or virtually down. They see, oh, I'm in the M section. And so which side is John Harvard to the left or to the right? So he's to the left. So I could literally now, Jesus Christ. We talked about this before class, that this might be more, oh my God. There we go. We can tear the problem in half. Thank you. It's been a while. We can tear the problem in half. We know that John Harvard is to the left, so I can throw half of the problem away if dramatically, such that I'm now gone from a 1,000-page problem to 500 pages instead. What now can I do? I can go roughly to the middle here, and maybe I'm in the E section. So I went a little too far back to the left, but I kept it simple, and I just divided so that I can conquer this problem, if you will. And if I'm in the E section now, is John Harvard to the left or to the right? To the right, so I can again, Jesus Christ. tear the problem in half. And now, thank you. So now John Harvard, again, is going to be in this half. I can throw this half away. So now I've gone from 1,000 to 500 to 250. And I can repeat down to 125, half of that, half of that, half of that, until I'm left with, finally, just a single page. And John Harvard is hopefully now on this page such that I can call him, or not at all, at which point this is all sort of for naught. But what's powerful about each of those algorithms is that they're sort of good, better, and best. Like they all get the job done, conditional on the second one having that little fix, just to make sure I don't miss John Harvard between two pages. But they're fundamentally different in their efficiency and the quality of their design. And this is really representative of one of the emphases of a class like this. It's not just about writing correct code or getting the job done, but doing it well and doing it quickly, using the least amount of CPU or computing resources, using the minimal amount of RAM, using the fewest number of people, using the least amount of money. Whatever your constrained resource is, solving a problem better. So that first algorithm, step-by-step instructions, was all about doing something like this, whereby the first algorithm, if we plot things on a grid like this, we have on the x-axis a representation of the size of the problem. So this would mean small problem, like 0 pages. This would mean big problem, like 1,000 pages. And on the y or vertical axis, we have some measurement of time. So this is the number of seconds or the number of page turns, whatever your metric actually is. So this would be not much time at all, so fast. This would be a lot of time, so slow. So what's the relationship if we just roughly draw these three algorithms? Well, the first one is technically a straight line. And we'll describe that as n. The slope is n, because if you think of n as a number for the number of pages, well, there's a one-to-one relationship in the first algorithm as to how many times I have to turn the page based on how many pages there actually is. And you can think about this in the extreme. If I was looking for someone whose name started with Z, I might have to go through like 1,000 darn pages to get to that person whose name started with Z, unless, again, I do something hackish and just kind of cheat and go to the end. If we execute these algorithms again and again the same way, that's going to be pretty slow. But the second algorithm was pretty much twice as fast, plus that one extra step potentially, but it's still a straight line. Because if there's 1,000 pages, and I'm dividing the problem, I'm doing 2 pages at a time, well, that's like n divided by 2 steps, plus 1, give or take. But it's still a straight line but it's still better. Notice, if this is the size of the problem, 1,000 pages for instance, we'll notice that the first algorithm took literally twice as much time as the second algorithm. So we're doing better already. But the third algorithm, fundamentally, is going to look something like this. And if you remember your logarithm, so to speak, sort of the opposite of an exponential, this curve is so much lower and flatter, if you will, than either of these two. Mathematically, more on this another time, the slope is going to be like log base 2 of n, or just logarithmic in nature. But what it means is that it's growing very, very, very slowly. It's still going up. It's never going to flatline and go perfectly horizontal, but it goes up very slowly. Why? Well, if you think about two towns nearby, like Cambridge on this side of the river and the town of Alston on the other, suppose that they still have phone books like this one, and they merge their phone books for whatever reason. So overnight, we go from a 1,000-page phone book to a 2,000-page phone book. The first algorithm is going to take literally twice as long, as will the second one, because we're only going through it 1 or 2 pages at a time. But if the phone book size doubles from this year, for instance, to next year, you can kind of, in your mind's eye, think about the green line. It's not going to go up that much higher. Why? Well, practically speaking, even if the phone book becomes 2,000 pages long, well, how many more times do you have to tear or divide that problem in half? Just one, because you're taking a 1,000-page bite out of it, or 500, then a 250. You're taking much bigger bites out of it than just 1 or 2 at a time. And so what computer science and what algorithms and about good design is about is figuring out what is the logic via which you can solve problems not only correctly, but efficiently as well. And that then gives us these things called algorithms. And when it comes time to code, which we're about to do too, code is just an implementation in a language the computer understands of an algorithm. Now, this assumes that we've come up with some digital way, that is to say 0 and 1 based way, to represent names and numbers. But honestly, we already did that. We came up with ASCII and then Unicode to represent the names. Representing numbers is even easier than that. That's really where we started. So code is just about taking as input some standardized representation of names and numbers and spitting out answers. And that's truly what iOS and Android are doing. When you start doing autocomplete, they could be searching from the top to the bottom, which is fine if you've only got a few friends and family in the phone. But if you've got 1,000, or if you've got 10,000, or if it's not a phone book anymore, it's some database with lots and lots of data, well, it stands to reason that it'd be nice maybe if the computer kept it all alphabetized, just like that book, and jumped to the middle, then the middle of the middle, then the middle of the middle of the middle, and so forth. Why? Because the speed is going to be much, much faster, logarithmic in nature, and not linear, so to speak, in nature. But we'll revisit those topics as well. But for now, before we get into actual code, let's talk for a moment about pseudocode. So pseudocode is not one formal thing. Every human will come up with their own way of representing pseudocode. It's an English-like or human-like formulation of step-by-step instructions, just using terse, correct English, or whatever human language. So for instance, if I want to translate what I did somewhat intuitively with that phone book by just dividing in half into step-by-step instructions I could hand you, or nowadays like a robot or something like that, well, step 1 was essentially to pick up the phone book, which I did. Step 2 was I opened to the middle of the phone book in the third and final algorithm. Step 3 was look at the page, as I did. Step 4 got a little more interesting. Even though I didn't verbalize this, presumably I was asking myself a question. If the person I'm looking for, John Harvard, is on the page, then I would have called him right then. But if he weren't on the page, if he instead were earlier in the book, as did happen, well, then I'm going to go to the left, so to speak. But more methodically, I'm going to open to the middle of the left half of the book. Then I'm going to go back to line 3. That's interesting. We'll come back to that in a moment. But else, if the person is later in the book, well, I'm going to open to the middle of the right half of the book and then go back to line 3. Now, let's pause here. Why do I keep going back to line 3? This would seem to get me doing the same thing forever, endlessly, but not quite. Why? Yeah, so because I am dividing the problem in half, for instance, on line 6 or line 9, implicitly, just based on how I've written this, the problem's getting smaller and smaller and smaller. So it's fine if I keep doing the same logic again and again, because if the problem's getting smaller, eventually it's going to bottom out, and I'm going to have just one person on that page that I want to call, and so the algorithm's done. But there is a perverse corner case, if you will, and this is where it's ever more important to be precise when writing code and anticipate what could go wrong. I should probably ask one more question in this code, not just these 3. What might that question be? Yeah. Yeah, so if John Harvard is not in the book, there's this corner case where what if I'm just wasting my time entirely and I get to the end of the phone book and John Harvard's not there? What should the computer do? Well, as an aside, if you've ever been using your Mac or PC or phone and the thing just freezes, or like the stupid little beach ball starts spinning or something like that, and you're like, what is going on? Some human at Google or Microsoft or Apple or the like made a mistake. They forgot, for instance, that fourth uncommon but possible situation wherein if they don't tell the computer how to handle it, the computer is effectively going to freak out and do something undefined, like just hang or reboot or do something else. So we do want to add this, else quit altogether. So you have well-defined behavior. And truly think that the next time your computer or phone spontaneously reboots or dies or does something wrong, it's probably not your fault per se. It's some other human elsewhere did not write correct code. They didn't anticipate cases like these. But now let's use some terminology here. There's some salient ideas that we're going to see in Scratch and C and Python and these other languages I alluded to earlier. Everything I've just highlighted here, henceforth, we're going to think of as functions. Functions are verbs or actions that really get some small piece of work done for you. Functions are verbs or actions. Here, though, highlighted is the beginning of what we'll call conditionals. Conditional is like a fork in the road. Do I go this way? Do I go this way? Or some other way altogether? How do you decide what road to go down? We're going to call these questions you ask yourself Boolean expressions, named after a mathematician, Boole. And a Boolean expression is just a question that has a yes or no answer, or a true or false answer, or a 1 or 0 answer. Just it's a binary state, yes or no, typically. Otherwise, we have this, go back to, which is what we're generally going to call a loop, which somehow induces cyclical behavior again and again. And those functions and those conditionals, Boolean expressions and loops and a few other concepts are pretty much what will underlie all of the code that we write, whether it is in Scratch, C, or something else altogether. But we need to get to that point. And in fact, let's go and infer what this program here does. At the end of the day, computers only understand zeros and ones, so I claim here is a program of zeros and ones. What does it do? Anyone want to guess? I mean, we could spend all day converting all of these zeros and ones to numbers, but they're not going to be numbers if it's code. What do you think? That's amazing. It does, in fact, print hello world. All right, so no one, except like maybe you and me and a few others in the room, should know, and that was probably guess, admittedly, or advancing on the slide. But why is that? Well, it turns out that not only do computers standardize information, data, like numbers and letters and colors and other things, they also standardize instructions. And so if you've heard of companies like Intel or AMD or NVIDIA or others, among the things they do is they decide as a company what pattern of zeros and ones shall represent what functionality. And it's very low-level functionality. Those companies and others decide that some pattern of zeros and ones means add two numbers together, or subtract, or multiply. Another pattern might mean load information from the computer's hard drive into memory. Another might mean store it somewhere else. Another might mean print something out to the screen. So nested somewhere in here, and admittedly I have no idea which pattern offhand because it's not interesting enough to go figure it out at this level, says print. And somewhere in there, like this gentleman proposed, I bet we could find the representation of H, which was 72, and E, and L, and L, and O, and everything that composes hello world. Because as it turns out, in programming circles, the very first program that students typically write is that of hello world. Now, this one here is written in a much more intelligible way. Even if you're not a programmer, odds are if I asked you, what does this program do, you would have said, oh, hello world, even though there's a lot of clutter here. Like, no idea what this is until next week. Int main void, that looks cryptic. There's these weird curly braces, which we rarely use in the real world. But at least I understand a few words like hello and world. And this is kind of familiar, printf, but it's not print, but it's probably the same thing. So here, too, is an example of this hierarchy. Back in the day, in the earliest days of computers, humans were writing code by representing zeros and ones. If you've ever heard your parents talk about punch cards or the like, you're effectively representing patterns that tell the computer what to do or what to represent, like literally holes in paper. Well, pretty quickly early on, this got really tedious, only writing code at such a low level. So someone decided, you know what? I'm going to put in the effort. I'm going to figure out what patterns of zeros and ones I can put together so as to be able to convert something more user-friendly to those zeros and ones. And as a teaser for next week, that person invented the first compiler. A compiler is just a program that translates one language to another. And more modernly, this is a language called C, which we'll spend a few weeks on together because it's so fundamental to how the computer works. Even this is going to get tedious by like week 6 of the class. And this is going to get stupid. This is going to get annoying. This is going to get cryptic. We're just going to write print hello on the screen in order to use a different language called Python. Why? Because someone wrote in C a program that can convert Python, this is a white lie, to C, which can then be converted to zeros and ones, and so forth. So in computing, there's this principle of abstraction, where we start with the basics, and thank God we can all trust that someone else solved these really hard problems way long ago. Then they wrote programs to make it easier. We write programs to make it easier. You can now write code like I did with the chatbot to make things even easier. Why? Because OpenAI and other companies have abstracted away a lot of the lower level implementation details. And that's where I think this stuff gets really exciting. We can stand on the shoulders of others so long as we know how to use and assemble these kinds of building blocks. And
Hey everyone, and welcome to today's Explainer. I am absolutely thrilled to jump into this with you. You know, if you've ever looked at a computer screen full of programming code and thought, wow, that looks like a terrifying, indecipherable wall of complete gibberish, well, you are definitely not alone. Honestly, it can feel like trying to read a lost, ancient language. But what if I told you that you actually already think like a coder, literally every single day? It's true. In this explainer, we're going to demystify the whole world of programming. We'll break down the logic that powers our digital world and show you exactly how it perfectly mirrors the normal, logical steps you take in your daily life.
So, here is our roadmap for today. We're going to hit everyday algorithms in action, the quest for efficiency, pseudocode, the coding bridge, programming's basic building blocks, and finally, putting it all together. Okay, ready? Let's dive right in.
All right, starting off with Section 1, Everyday Algorithms in Action, Solving Problems in the Physical World. Let's ground this whole abstract concept of coding into a totally mundane physical task. Imagine, if you will, a giant pile of unmatched socks that just came out of the laundry for a family of 5. It is just an absolute mountain of cotton. A terrifying, chaotic mess sitting right there on your living room floor. Now, what's your specific strategy for matching them? You probably don't just grab a single sock blindly and then dig around the massive pile completely at random hoping to find its exact twin, right? No way! Doing it that way would take you hours, and honestly, you'd probably just give up halfway through.
Instead, you likely use a highly structured process to conquer that mountain. Step 1, you might sort all the socks into broad piles by color. You know, all the blacks here, all the whites over there. Step 2, you sort by size within each of those color piles to separate out the kids' socks from the adults. And step 3, you match the exact pairs and store them away, basically repeating this loop until the entire pile is just gone. Sorting by color first, rather than picking randomly, is a highly logical process, and it saves an enormous amount of time. You've taken a chaotic input, processed it with your own internal rules, and achieved your desired organized output.
And actually, that brings us right to our first technical definition, because that structured sock sorting process you do on autopilot, that is exactly what an algorithm is. In computer science, an algorithm is simply a set of step-by-step instructions or logical, well-defined rules that detail a process to efficiently and accurately solve a problem. Just think of it as an action plan, kind of like a recipe. Whether you're baking a cake, navigating your morning traffic, or matching socks, if you're following a structured set of instructions to reach a goal, you are absolutely already executing an algorithm.
Moving on to Section 2, the quest for efficiency. Working smarter, not harder.
So while multiple algorithms can solve the exact same problem, like, different ways of sorting those laundry socks, computer science is obsessed with finding the absolute fastest, most efficient route. Imagine trying to find the name Marcus Smith in an old, massive physical phone book. A linear search means starting at page 1 and flipping through the book one single page at a time. If Marcus is way back on page 550, well, that's 550 flips. It works, for sure, but it is painfully slow. But a binary search? That is ruthlessly efficient. You open the book exactly in the middle. You check if Smith is in the first half or the second half alphabetically. If he's in the second half, you completely ignore, like theoretically just tear away and throw out, the entire first half of the book. Then you split the remaining half in the middle again, and you just repeat this exact same process until you find him.
Check this out. If that phone book has 1,000 pages, utilizing the binary search algorithm guarantees you will find any name in a maximum of just 10 flips. Let that sink in for a second. Just 10 flips to search 1,000 pages. How? Because dividing 1,000 in half repeatedly gets you down to one single page incredibly fast. 2 to the power of 10 is 1,024. By just tweaking the logic of how we search, we go from potentially 1,000 tedious steps down to a maximum of 10. It is a mind-blowing leap in efficiency, and it perfectly highlights why picking the right algorithm matters so much.
Which brings us to Section 3, Pseudocode, the coding bridge, translating human logic for machines. Okay, so we've established that algorithms are just human logic. But actual programming languages like Java, Python, or C++, they can look terrifying. To get from our everyday human logic over to their machine syntax, we use something called pseudocode. The prefix pseudo just means fake or mock, so literally, mock code. Think of it as the ultimate bridge. It's an informal, high-level outline of an algorithm written in a combination of plain English and basic code structure. And the best part? It is completely independent of any specific programming language. This is incredibly freeing, because it lets us map out our brilliant algorithms without worrying about strict, confusing coding grammar, like, whether we missed a semicolon or used the wrong bracket. Let's see how this works in practice. Imagine a simple pseudocode block for adding two numbers together. We declare the program name, we take an input for number 1, we take an input for number 2, then we create a rule that says sum equals number 1 plus number 2, and then we simply output the sum. Finally, we tell the program to end. Notice how neatly it's indented? It flows almost exactly like plain English, giving us this really clear, step-by-step outline that any programmer could instantly understand and later translate into real, functioning software code.
All right, Section 4, Programming's Basic Building Blocks, the Tools of the Trade.
When we actually write pseudocode, we rely on a few core structural tools to mimic how a computer actually processes information and makes decisions. And these are universal tools. You'll use them no matter what programming language you eventually learn. We have variables, which are basically just little containers or buckets for storing values, kind of like our sum from a minute ago. We have conditionals, which are your if, then, and else statements. We have Boolean expressions, which is just a fancy way of saying we check if something is true or false. And we have loops, which tell the computer to repeat an action until a specific condition is met, just like how we kept matching socks until that laundry pile was completely empty.
Let's look a little closer at a conditional statement, using another everyday algorithm. Let's say you receive an invitation to a weekend party. How do you decide whether to go or just stay home? Well, you check your conditions. If your best friend is going to the party, then you prepare to go and have a great time. Else, meaning if they aren't going, you politely decline and stay on the couch. Then you end your decision process. See? You are running these exact if, then, else conditionals in your head every single day without even realizing it.
Which leads us nicely into Section 5, putting it all together. Solving the alien challenge.
Let's test everything we've learned today. Imagine an alien lands on Earth, right? And they challenge you to write a program that checks if any given number is even or odd. First, we need our underlying mathematical algorithm. We can use a super handy mathematical tool called the modulo operator, which simply divides a number and spits out the remainder. So 3 modulo 2 leaves a remainder of 1. It's an odd number. 4 modulo 2 leaves a remainder of 0. It divides perfectly, so it's even. 5 modulo 2 is 1, 6 modulo 2 is 0. Look at that, we've found our algorithmic pattern. If the remainder is 0, the number is definitely even. If the remainder is 1, the number is definitely odd.
Now, let's translate that math logic right into beautifully structured pseudocode using those conditional building blocks we talked about. We input a number. If that number mod 2 equals 0, then we output the number is even. Else, we output the number is odd. And if. Look how incredibly clean and readable that is. By breaking the problem down, we created a perfect blueprint that completely solves the aliens challenge before we've even touched a real programming language.
And honestly, this exact same logical structure is used everywhere in the real software you interact with daily. Take calculating a shopping cart discount at your favorite online store, for example. You input the customer's cart total. If the total is strictly less than $100, then you output, you do not get a discount. Else, you output, you do get a discount. And if. Whether we're calculating automated store discounts or checking if alien numbers are even or odd, we're really just applying logical rules to inputs to get our desired outputs.
Which leaves us with one final thought for you to take away. Learning to code isn't really about memorizing confusing syntax, obscure grammar, or weird punctuation right out of the gate. It is simply about taking your natural, everyday logical thinking and giving it a formal structure. If you can logically and efficiently sort a pile of laundry using loops, and if you can use conditions to decide whether to attend a party, you are absolutely already thinking like a programmer. So the only question left is, now that you know the underlying logic, what tedious part of your own life are you going to write an algorithm to automate next? Keep that in mind, and thanks so much for joining me on this explainer.